Yes, perfectly.
Excellent. We are really delighted to have you. This is, as I just said, without the microphone failing technology. This is Goncalo Tabuada, who's going to speak to us about the non-commutative generalized Riemann hypothesis. And we are really stoked that we are able to make this happen in this distributed fashion.
Okay, thank you so much. I would like to start by thanking the organizers for the invitation to speak at this workshop. It's a great pleasure, a great honor. Also, I'd like to thank them for allowing me to give the online talk. It's impossible, unfortunately, it's impossible for me to be physically present there. So I would like to talk about the Riemann hypothesis. I mean, my talk will not be directly related with mathematical physics, but I mean, since this is such an important topic, I hope that is still of interest to the audience. So I prepared the talk in order to be accessible to everyone. So please interrupt me and ask questions. Okay, so even the very first thing I would like to say is that, well, I will use the words Riemann hypothesis quite often. So I will simplify by just writing RH and also the word non-commutative. So I will just write NC. And so let me start by explaining the title. So I would like to start by explaining what do I mean by Riemann hypothesis. Well, this is standard. So we start with the Riemann zeta function, which is defined as this infinite sum going from 1 to infinity of 1 over ns as a complex variable. And what we know about this function, well, we know several things. We know that it converges absolutely on the half plane where the real part of S is greater than 1. We also know that it has Euler product. We can express it as a Euler product. So more concretely, we can write it as a product over all primes of 1 over 1 minus p minus s. And moreover, we know that this function that is well defined in this half plane, it actually admits a meromorphic continuation. To C, to the entire complex plane. And so we have the following picture. So we can draw the following. This picture. So we have the 0, 1, 1 over 2. And so here we have so the function is well defined in this region, this half plane, and it actually admits a meromorphic continuation to the entire plane. And so it actually has a pole at 1, which is a simple pole. And then what is the content of the Riemann hypothesis, which goes back to Riemann to 1859. It says that if you have a 0 of this function, and if you restrict yourself to the critical stripe, so where the real part of S is between 0 and 1, then it's because this 0 actually lands in this line where the real part is 1 over 2. So in other words, we are actually, this is the region where we expect the zeros of the Riemann zeta function to land. So this is well known, and even Riemann at the time established a precise relation between this formulation of the Riemann hypothesis and the distribution of prime numbers. Well, this is what I meant by Riemann hypothesis. So now let me explain or recall what is the generalized Riemann hypothesis. So this I will follow Jean-Pierre Serre. So generalized Riemann hypothesis. So we now are working over little k will be a global field. So this will be a vast generalization of the classical Riemann hypothesis. And we have a scheme which will be a smooth proper k scheme. And we'll choose an integer between 0 and twice the dimension of our scheme, which will be the weight that we are considering. So let's just focus first on the global field. So let me recall. So there will be quite a lot of notations. We'll start with some important notations. So let me recall you. So little k, it's a global field. So as you all know, that means that in characteristic 0, it is a finite extension of the rational numbers, so a number field. And in positive characteristic, it's just a finite extension of the field of rational functions over a finite field. And now what one can do whenever we have a global field, we can look, we denote by sigma little k, so this is Serre's notation, the infinite, this infinite set of non-Archimedean places, of non-Archimedean places of our field. And whenever we have a non-Archimedean place, let's call it mu, we can assign several different things to it. So first of all, we can look at the completion. So let's denote it like this. So the completion of our field at that non-Archimedean place. We can look at O of mu, the evaluation ring, the associated evaluation ring of this completion. Then we can denote by, so let me write it like this. So mu, the residue field of this local ring, so the residue field of this local ring. And then we can look at, denote like this, the characteristic of this residue field, which will actually be a finite field. And so, since it's a finite field, we denote like this, the cardinality of this finite field. So maybe, well, this is pretty abstract. Let me make a very concrete example. So if we are in the particular case where our global field is the rationals, so where the global field is the rationals, so in that case, this infinite set of non-Archimedean places, it's actually in bijection with the prime numbers. So this corresponds to a prime number, an element here, a non-Archimedean place, it's a prime number. The completion of Q would correspond to the p-adic numbers. The evaluation ring would be the p-adic integers. The residue field would be the quotient of Z by PZ. In this case, the characteristic is P, and also in this case, the cardinality is also P. So in the other cases, it will be slightly more complicated. And now, still a little bit of notation. So it turns out that you can look at the absolute Galois group of this completion. So you take the absolute Galois group of this completion, and then this maps canonically to the absolute Galois group of the residue field. And there is a kernel here, and this kernel, it's what it's usually called the inertia. So the inertia group, this is the inertia group at this non-Archimedean place. And here, well, the residue field is a finite field, so we actually know that this, it's Z hat, so it's isomorphic to Z hat. And inside, we can look at this arithmetic Frobenius. So if you have an element, you can raise it to the power given by the cardinality of your finite field. So this gives you this topological generator of this profinite group. and then you can look at the inverse of this arithmetic Frobenius, and that's what we call the pi of mu, which is usually called the geometric Frobenius. And now, from now on, we make a choice. We need to choose a prime number. So the prime number L mu different from the characteristic of at P mu, and also we need to choose a field embedding. Of the, which are called iota mu, going from the Q L mu inside of C, and we need to do this for every non-Archimedean place. Okay, this is what I wanted to say about the notation. So we actually need all these notations to define the L functions following Serre. So how is the L function defined for following Serre? So we have this definition of Serre. So the L function of this weight of my algebraic variety, and the variable is S, is defined as this infinite product over all non-Archimedean places, and where I have this Archimedean factor of my x S. And how is defined this Archimedean factor? Well, what one can do is the following. So I'm going to take the inverse. So I can start by looking at the étale cohomology of this weight of my x. So by x, I start by base changing it from k to the completion. But then that's not good enough because I want a geometric theory. So so I still need to base change that to the algebraic closure. And then I take coefficients of my étale cohomology group in QL mu. So this, I'm using this prime, which is different from P mu. So I do this, and then what I do is that here you see that the absolute Galois group of the completion acts here. And so if I restrict myself to those elements that are invariant under the inertia subgroup, then I have a canonical action of this absolute Galois group of the residue field. So in particular, I have an action of this element, this pi mu, this geometric Frobenius, acting on this vector space. So I can simply take its characteristic polynomial. But that's not going to be enough, because what I want to do if I have the characteristic polynomial is to replace t by complex. I want to use complex conjugation. So and that's why I really need this field embedding to make this work. So let me be more precise. So here I could take the determinant of 1 minus. So here I have my automorphism of this vector space. So I need actually to base change to C using my embedding that I've chosen. So now it's going to act here when I base change to C. And now I can do the following. If I usually should have T here to have the characteristic polynomial, but what we want to do now is to replace my T by, I want to replace it by doing the cardinality of my finite field and then minus S. So since I've base changed to C, now all this makes sense. So I have this well-defined function here. And well, and this is my L function of weight W, or omega, if you want. And so what can we say about this, function? So this theorem of Serre tells us the following, that this function here, it's actually a meromorphic function. So it's a meromorphic function on this half plane given by the real part of S is actually greater than the weight over 2 plus 1. So if you want, one picture that one could make is the following. So we have, as before, so we have this picture. Here we have 0 here we have omega over 2, here we have omega over 1 over 2, and omega over 2 plus 1. So the function, it's well defined in this region here. So it's well defined in this region. Okay. And what can we say about this function? Well, there are two conditions now that are expected to hold about this function. So condition number one is that this function should admit a meromorphic continuation to the entire complex plane. So it admits a meromorphic continuation to C. And the second condition is that this function, it's expected that it has no poles on this critical stripe. Means that when the real part of my S sits between omega over 2 and omega over 2 plus 1. So in this region, this again, in this region here, this critical stripe, it's expected that there are no poles here. What can you say about these conditions? Well, if we are in characteristic 0, these two conditions hold in several cases for certain zero-dimensional varieties, for certain elliptic curves, for certain modular curves, for certain Chimura varieties, etc. And if we are in positive characteristic, so if we are in the case of a function field, it's actually the conditions hold all the time. It's actually a result of Grothendieck. So we have these two extreme cases, and now we can consider finally what do I mean by the generalized Riemann hypothesis. It is, which I will denote from now on like this, R omega x. So this means that if I have a zero of this function, so if this function vanishes with the variable belonging to this critical stripe, then it's because the zero is actually in this specific line. So in other words, the zeros are expected to land here in this red line. So, well, you see, as you might already see, this is really a very vast generalization of the classical Riemann hypothesis. Let me just explain that. Why is that the case? Well, if you take this very simple example, this baby example of take the example of the field being the rational numbers, and you take for x the simplest thing that you could have, meaning the point, spec of q, and here the weight, well, there's no possibilities, is degree 0, the only possibility is degree 0. Here, it turns out that when you look at this L function for the spec q, with what you get, if you follow the definition, is precisely this Euler product. I'm sorry, it's precisely this product, this infinite product. So this product over primes of 1 over 1 minus p minus s, and that is nothing but the classical Riemann's at the function, where you sum over 1 until infinity, that 1 over minus s. So you see that in this very, very, very simple case, you recover the classical Riemann hypothesis. And another interesting example, let's say that now we are working still in characteristic 0, but you are working in a number field. And again, you take for x the simplest thing, you take the spec of your number field, and the weight, the only possibility is 0. Here, the L function that you get in this case, it's this classical Debkin zeta function where you take the sum over all ideals inside of the ring of integers of your number field, and you take 1 over the norm of your ideal. And this is sometimes called the extended Riemann hypothesis in this particular case of number fields. So you see, what can we say about this conjecture? So what is the status of this generalized Riemann hypothesis? Well, the status depends drastically on the characteristic. So if we are in characteristic 0, absolutely no cases are known. No cases are known. Of course, you see the simplest case, it's this one over Q and just a point. That's the classical Riemann hypothesis. So we don't know absolutely nothing in characteristic 0. And how about in positive characteristic? Well, in positive characteristic, it was proved. It is known, and it follows from the work of Grothendieck and Berlin. So we have this extreme cases. So in characteristic 0, nothing is known. In positive characteristic, everything is known. Okay, so this is what I wanted to say about the generalized Riemann hypothesis in my title. And now let's move on and let's try to explain what do I mean by the non-commutative version of this generalized Riemann hypothesis. So what do I mean by that? So I want to go in this direction to have some kind of non-commutative version of the Riemann hypothesis. So let me just talk a little bit about non-commutative geometry. Non-commutative geometry, so for different people, means different things. I will follow this perspective of Manin and the Moscow school. So we are working just over a field, any field, and you have this notion, so you have this definition, which goes back to Bondal and Kapranov, of what is a differential graded category, so sometimes called a DG category. And this is nothing but a category which is enriched over complexes of k-vector spaces. Example, whenever you have an algebra, so whenever you have a k-algebra, or more generally, whenever you have a differential graded k-algebra, well, that's naturally a DG category, if you want, with a single object. It's the same thing. So it's interesting because this notion captures all algebra somehow, and also geometry, because whenever you have a scheme, a k-scheme, you can look at the perfect complexes on your scheme, and that carries the DG structure. So it carries also, that also gives rise to a differential graded category. Well, so somehow it's a setting where you can talk simultaneously about algebra and geometry. Okay. So the most famous example of this philosophy of non-commutative geometry goes back to Beilinson. So it's this famous example. So when you look at the perfect complexes on the projective line, so this category is very far from being the category of modules over an algebra. But as soon as you go to this drive setting and you consider this DG enhancement, it turns out to be a Merritt equivalent to an algebra, but a non-commutative one. It's actually isomorphic to the algebra of matrices of this form. So you see in this world of non-commutative geometry, the projective line becomes affine, becomes given by an algebra, but by a non-commutative one. So this is some kind of the phenomenon that's occurring in this world where algebra and geometry become interconnected. And for today, I'm going to use this notion, which was introduced by Orlov. If you have a DG category, so suppose that you have a DG category, you say that it's called a geometric non-commutative scheme. So geometric non-commutative scheme. So that means that, by definition, that means that there exists a smooth proper k-scheme X, and moreover, the property that our category A, our DG category A, can be embedded in the perfect complexes of our scheme, And well, this embedding needs to satisfy a technical condition, and it needs to be admissible. In other words, means that well, this inclusion needs to admit some kind of left and right adjoint. So this X is not necessarily unique. We're just saying that, well, this category sits inside the drive category of a truly geometric object. So you call it geometric non-commutative scheme. And it's interesting because a lot of non-commutative objects are actually geometric in this sense of Orlov. For example, if you have a finite dimensional K algebra, which is of finite global dimension, and suppose that also that when you mod out A by its Jacobson radical, you have this K algebra is K separable. So this is something that holds, for example, whenever you are working with a perfect field. Then it turns out, so this is the result of Orlov, that this A, it's a geometric non-commutative scheme. So any finite dimensional algebra of finite global dimension, actually you can embed it inside the drive category of a scheme. So, but those things are not schemes. For example, let me give you a very baby case. So let's say take the following quiver, simple quiver where you have two vertices and one arrow. And then if we have a quiver, you can look at the associated quiver algebra. So the algebra generated by this quiver, well, this is very simple. It's just the algebra of matrices of this form. And it turns out that this algebra is such a simple algebra. It's not Morita equivalent to any category of perfect complexes on Y with Y a smooth projective scheme. And so it's not the drive category of a scheme. And this, the one reason for this, one way to see this is that this thing here, it's actually Calabi-Yau. So you can talk about Calabi-Yau dimension in great generality. It turns out that this algebra here has a fractional Calabi-Yau dimension of 1/3. And the Calabi-Yau dimension of any algebraic varieties is always an integer. So this cannot be the drive category of a scheme. So you see it's inside the drive category of a scheme, but it's not one of those. So there exist truly non-commutative schemes, non-commutative geometric schemes, which are not schemes themselves. Okay, and so the idea now is to try to do or to have a version of L functions and of the Riemann hypothesis for in this generality. So this clearly generalizes schemes. So let's see if the Riemann hypothesis also makes sense in this generality. So for this, I need to have some kind of a non-commutative analog of the Tal cohomology, or if you want, of the Eladic cohomology. So what is the non-commutative Eladic cohomology? So one possibility here, so once again, suppose that we are working over the field, and I'm going to choose a prime number. I need to choose a prime number, let's say L, different from the characteristic of my field, and I have a geometric non-commutative scheme, and I would like to define for A some kind of non-commutative Eladic cohomology. So one thing that you can do is use K theory. So you can take the étal, so the Eladic étal K theory of A. So you have A, and you can do the Eladic K theory, étal K theory of A, which you define as follows. So let me write it and then explain. So the calling N, and then you do this, and then the K theory with coefficients. Yes. So you start with non-connective K theory, which is a spectrum. Then you do this mod L mu. So again, a spectrum. Then you do this localization with respect to Ku, the topological complex K theory spectrum. And then you do this homotopy limit, an homotopy limit, an homotopy limit. And you end up with this spectrum, which is this Eladic étal K theory. And using this, you can make the following definition. You can define, take the following definition. You can define even Orlov cohomology theory, so this with respect to this chosen L. So what you do is that you take the pi naught of this spectrum. So you take the total K theory of your A. I want to have a geometric theory. So first I base change to the separable closure. And then I extract this. And then I still need to invert L. And then I invert L. And I can have also an odd version with respect to L, where I take the pi 1 of this Orlov K theory. So first I go to the separable closure, and then I invert L. And well, what do I end up with this? Well, the remark is that these groups, these are finite dimensional QL. So they are Q linear, like Q linear modules over the absolute Galois group. So clearly, the absolute Galois group acts here, and they are finite dimensional QL vector spaces equipped with this action. And using them, we can define the non-commutative L functions. So we can define these non-commutative L functions as you expect. So now I'm in the case of a global field. And again, what's happening is that I don't have a smooth projective scheme, but I have a non-commutative geometric scheme. Yeah. And what am I going to do? And again, it makes no sense to talk about weight because I just have a DG category. So what I can do is I can define an even and odd L function. So I can define an even L function. And I define it as, again, as a product over all the Archimedean places of my global field, where I have these factors. And then how is each factor defined? Well, is as you expect. So this factor here, you do a similar construction. So you take now the even Orlov for the even. So you take these even groups that you've just defined, and then you need first to base change to the completion, and then you take those things that are invariant under the things that are fixed under the inertial group. Then again, you need to base change. You need to extend scalars to C, and here you have this operator. So you have this similar formula where here you have this operator, and you need to base change to C to make this sense, and yeah, you get this well-defined function. And similarly, same story for the odd parts, where here instead of even homology, you take the hot homology. So you can also define this one. Okay. So we have these two. You can assign to any non-commutative geometric scheme two L functions, an even and an odd one. And now you have the following analog of this the theorem of Serre. So we have the following analog is that in fact this function, this even function and this odd L function, they are in fact this is a meromorphic function. It's a meromorphic function on the half plane, on this half plane, where here it's where the real part of S is actually greater than 1, and here where the real part of S is greater than 3 over 2. So let me make a picture about these two functions. So here I have the even one, and here I have the odd one. And so we can have the following picture. So once again, here, so I have 0 I have 1 1/2.
So sorry, can I interrupt you?
Yes, of course.
There was a question in chat a couple of minutes ago asking
Okay.
about the n that you took the co-limit over.
Yes.
Could you talk a little bit about just where that n came from?
Yeah. Sorry. Yeah, absolutely. That's yeah, sorry. This makes no sense. It's a typo. In fact, there's no mu here. It's a typo. Sorry. This is not a mu. It's an n. Sorry. Of course. The mu, it's a non-Archimedean place. Sorry. So it's just a typo. Okay. You make the quotient by powers of your prime. Sorry.
Thank you.
Thank you for the question. That's absolutely. Okay, so here I have where is I? Yes, so here I have 0, I have 1/2, I have 1, I have 2, and so here I would like to make the following. So here, so this is well defined in this region, and here it's well defined in this region. So this is the picture. So what we have about these functions defined for any non-commutative geometric scheme, they're well defined in these regions. And now we can also phrase the non-commutative. We can phrase the non-commutative generalized Riemann hypothesis. So this is my title. Finally, I'm explaining my title. So I will write it like R even for A and the R odd for A. What does this stand for? Well, this simply means that this even L function or this odd L function, whenever I have a 0, and with when the case where I'm in this critical stripe, or in this critical stripe here, then this is going to imply that the 0 is actually in this line or in this line. So in other words, whenever I'm in this critical stripe, the zeros need to actually land here, and similarly, the zeros will need to land here. Yes. So yeah, and well, this ends the explanation of my title. And now, why I'm interested in this? So why is this useful? Well, I have the following result. So this theorem. Suppose that you have your favorite smooth and proper K-scheme. And I'm going to assume, so let's assume that the condition C2 is verified. So not only that, so I can look at the possible L functions of my X, and I can, so I'm always assuming that I have this meromorphic continuation. Otherwise, we cannot even speak about the Riemann hypothesis. But I'm assuming that there are no poles on these critical stripes. Then in this case, we actually have two things. So we can look at the Riemann hypothesis, the non-commutative version for the derived category of X, and also the odd version of this. And also we can also look at this Riemann hypothesis, so one for each one of the weights, in case the even weights, or each one for the odd weights. So it turns out that, well, if this Riemann hypothesis holds, then you also have the same result in a non-commutative setting, but the theorem tells us that the converse is also holds. So this is telling you more or less, or intuitively speaking, is telling you that the Riemann, the generalized Riemann hypothesis makes sense in this full generality, makes sense for any geometric non-commutative scheme, and in such a way that when you restrict yourself to classical schemes, you recover the classical Riemann hypothesis, or the generalized Riemann hypothesis. So it actually makes sense in a greater generality. Of course, that does not help to prove the generalized Riemann hypothesis, but it helps to establish properties about the generalized Riemann hypothesis of an ordinary scheme. So let me explain this. So this is another topic of my talk is to go towards applications of this non-commutative viewpoint on the Riemann hypothesis. So let me give applications of this viewpoint, applications to commutative geometry, so to classical algebraic geometry, commutative geometry. So in commutative geometry, okay, so we are working over a global field. So if it's characteristic 0, if it's positive characteristic, if it's a number field, we know that this is already proven. So let's restrict ourselves to characteristic 0. And now let's take two x and y, two smooth proper case schemes, and let's assume that they satisfy the condition C2. And then what can we say? Well, we can say the following. First result is that, or first application is that we have this derived invariance of my conjecture. So I have this derived invariance. So whenever these two algebraic varieties, they might be geometrically very different, but suppose that there is a relation not among themselves, but among their derived categories. So suppose that actually the derived categories are equivalent, and this equivalence is given by a Fourier-Mukai equivalence. So it's just a technical issue. Then in this case, it turns out that the Riemann hypothesis for one variety, if you want this family index on the weights, it's actually equivalent to the Riemann hypothesis for the other variety indexed on the weights. So we actually have an equivalence of Riemann hypothesis. So this is telling you that, well, if someone manages to prove this generalized Riemann hypothesis for one variety, this will give you automatically that it's true for all its derived partners. So we have this property of the conjectures. It's invariant under derived equivalence. And also, it's something more general. It's actually invariant under HPD duality. So this is a relation. So we have also this HPD invariance. So HPD stands for homological projective duality in the sense of Kuznetsov. So whenever you have a variety which is HPD dual to Y, so well, if they are HPD duals, in fact, they come equipped with maps towards projective space and towards the dual projective space. And then what you can do is that whenever you have a subspace of the dual, you can take linear sections in both of them. So first of all, you can take the linear sections. So you do this fiber product on the projective space with the projectivization of this orthogonal. And here you have this other linear section on the other side, where you do this fiber product over the dual with this projectivization of L. So you get two linear sections, and if X and Y are HP dual to each other in the sense of Kuznetsov, then there is a strong relation between the derived categories of these two linear sections. And so you can actually conclude from here. So this actually implies, once again, that the Riemann hypothesis of these linear sections indexed on these weights, they do not change. They are the same. They stay always the same, although the varieties may be very different, of different dimensions, etc. The Riemann hypothesis does not change. Well, there are many examples of homological projective dualities. I do not have time to talk about this. Let me just mention. Well, there is something called the Veronese-Clifford HPD duality. There is the Grassmannian Pfaffian duality. There is the Spinor duality. There is the determinantal duality, etc. So whenever you are in such a setting where you have these HPD duals, the conjectures do not change. So again, another property of the conjecture. Okay, and now for the very end, let me give also some applications of these viewpoints to non-commutative geometry. So applications to non-commutative geometry. So what do I want to say here? So again, let's say that we are working over a global field. And let's grab one of those geometric non-commutative schemes. So we know that one example is given by this finite dimensional K-algebras, which are of finite global dimension. And I need that the quotient by the Jacobson radical to be K-separable. So which is the case, for example, in characteristic 0. Then what you can do, so let's grab this, any one like this. So one thing that you can do is that you can look at V1, etc. until Vn. You can look at the simple modules over this quotient. So this is semi-simple. You have this finite number of simple modules. Then you can look at the endomorphisms of this simple modules. And these endomorphisms, they are going to be, since they are simple modules, they're going to be division algebras, division K-algebras. And then if they are division K-algebras, well, I can look at their associated centers. And these centers here, they are going to be actually, the centers are going to be separable. So finite separable field extensions. Finite separable field extensions of K. And well, if you start with any algebra, you look at these finite separable field extensions, and well, the result is the following: is that if you look at the Riemann hypothesis, the classical one associated to this zero-dimensional varieties, so Ki, and you take this for I to vary between 1 and n. So take the Riemann hypothesis for each one of these zero-dimensional varieties, then this family of conjectures implies the Riemann hypothesis, the even Riemann hypothesis for A. So the odd Riemann hypothesis for A, this is true for somehow easy reasons, but the even part actually follows from this classical generalized Riemann hypothesis. And so in particular, the corollary is that this conjecture here, so the Riemann hypothesis for A and even the odd version, it's actually true. So the Riemann hypothesis is true when you are in positive characteristic. So in positive characteristic, well, if you take any finite dimensional algebra, finite global dimension, such that the quotient is K-separable, which is a mild condition, in fact, and if you are in positive characteristic over a number field, well, the Riemann hypothesis is there. It is true then. And there are many other cases where you actually can prove that the Riemann hypothesis for truly non-commutative objects actually follows from the Riemann hypothesis for commutative objects. So this is one baby case, let's say. Well, yeah, that's what I wanted to say about this this perspective. So as a summary, let me just mention that, well, this viewpoint does not help, I should emphasize, to prove the generalized Riemann hypothesis, but it establishes properties of the conjectures, and also it allows us to go towards non-commutative geometry and try to attack what it's already known in the commutative world, try to attack those similar things in the non-commutative world. Okay, thank you so much, and I hope that this is of interest to the audience, and thank you for your time.
That's all. Thank you together. Does anyone have questions? I can carry you the mic.
Yeah, so thank you for your talk. I had a couple questions, but I guess what I'll say is the idea that when you transform a variety into another, the general Riemann hypotheses on both of this, like one implies the other, does that come from like invariance of like K theory stuff? And like in general, I mean, last year there was a paper of Clausen and I think Akil Matthew, like where they kind of broke up étale K theory into different pieces and sort of looked at it in different lights. I don't really understand the paper very well, but do you think that you can get like finer or like different theorems that way when you transform one variety into another, and so that their Riemann hypothesis, their non-commutative Riemann hypotheses are like similar, or is that not?
What I'm using here, it's actually basic. So what's in the board here? So this what's happening here is that I mean, what makes things work is this fundamental paper of Thomasson. So Thomasson showed that you can define this Elladic étale K theory, and then you can relate this Elladic K theory, Elladic étale K theory with Elladic étale cohomology via. So there is a relation, there is a spectral sequence, and if you are working rationally, that spectral sequence degenerates. So that's really what I'm using. So if you plug here in the place of a scheme, so perfect complex on the scheme, this is morally speaking giving you all the components of the Elladic cohomology theory, but it doesn't give you the individual pieces. It gives you all the even pieces and all the odd pieces, and then each one of them come with a certain twist. So this is the kind of phenomenon that when you pass from a scheme to the derived category, you somehow lose the twists. So when you do the L function, the non-commutative L function of the perfect complexes, so for example, where is the result? Here. What's happening is that the L function, this non-commutative L function of the perfect complexes, is morally speaking, you grab the individual L functions for the even weights. So let's consider the even non-commutative L function of perfect complexes. That's the same thing as grabbing each one of the L functions of even weights, and then you shift them towards the same position, and then you multiply them together. So you somehow lose the individual pieces of the L function. You shift them and multiply them together. But for the Riemann hypothesis, so you lose information. But for the Riemann hypothesis, which is about where the zeros are, you actually are not losing information. So that's why you can actually conclude. That's why you have this implication here. So if you know the Riemann hypothesis, the non-commutative version, you still know the classical version for each one of the pieces. So this is what's behind of this result. Yeah.
Okay, thank you.
I hope I answered more or less.
Yeah. I guess one thing would also be, so when I feel like now that I feel like last year there was some work on understanding étale K theory and breaking it up into things like I think it was topological cyclic homology and Selmer K theory. I mean, can you sort of talk about invariants or L functions that come from these kinds of things, or is it?
Yeah, I mean, it's more or less kind of work in progress. I don't have much to say, but that's one thing to explore. Yes, you're absolutely right. I should say that maybe in this line of thought, that, for example, one thing that you can do, since you mentioned one thing that you can do is think about, for example, what would be the analog of crystalline cohomology. And that is something that it's extremely well known nowadays, which is this, as you mentioned, this TP. So you have this, so the analog of the Riemann cohomology. So here on the non-commutative side would be the periodic cyclic homology. And so here you are somehow in characteristic zero. And you would like to have some kind of the analog of the crystalline, and this is the TP here. And then if you have this TP, for example, you can use it to define, for example, zeta functions. So you can define zeta functions when you are working over finite fields, for example. And using TP, and it turns out that this TP comes equipped with a very interesting operator. It comes equipped with this Frobenius. So you can actually talk about these zeta functions. For example, here there is no such a thing as a Frobenius, but here, yes. So something that you can explore. Yeah, and this is related to what you're saying. For example, the way things are defined here, you may wonder if whenever, so here is the definition, whenever you have good reduction, as in the commutative world, if you have a description of the cell function in terms of TP, because then you can go actually define it directly on the finite field, and you don't need to use this inertia subgroup. Yeah, these are things that are being explored at the moment, yes.
Thank you.
Are there other questions from the physical audience? I don't see any questions lingering in the chat either. So let me just thank you again. I really appreciate your coming here and being here with us on this record heat-breaking day in England, and hopefully a reasonable day where you are.
Thank you for your time.